Welcome to this video where we will do an example of nodal analysis that includes two independent voltage sources. Unlike the simpler example of nodal analysis with an independent voltage source, which we've already done, in this case not all of our voltage sources will be connected to our reference node, which complicates things and makes it somewhat interesting, but it turns out it's not that hard still. So let's go ahead. This is our circuit, and our goal for this circuit is to find all of the node voltages. And so we'll start just as following the set of instructions that we have for doing nodal analysis. The first thing is to define a reference node, and again we'll choose this node at the bottom. The next thing is to define our node voltages. So we have a node here, and we'll say the voltage at this node is V1. We have a node here, we'll say that the voltage at this node is V2. We have a node here, we'll say the voltage at this node is V3. And finally, we have a node over here, we'll say that the voltage at this node is V4. Okay, so we've actually completed step 2. In one sense, we're already halfway done. Now the next thing we need to do is look at each of the nodes and use the connections to the nodes to get equations that we can solve. We have 4 unknowns, V1 through V4, so we'll need 4 equations. So let's start by looking at node 1. You'll notice that we have a 5-volt source between node 1 and our reference node, which means that the voltage at node 1 will always be 5 volts. Okay? No matter what else happens in the circuit, this voltage source will keep the voltage at node 1 5 volts with respect to the reference node. So that was easy. That was kind of fun. Okay, let's look at node 2. We would like to apply Kirchhoff's current law at node 2, basically looking at the current leaving here and the current leaving here, but unfortunately we don't know what current is going to go through this 10-volt source. Similarly, at node 3 we'd like to apply Kirchhoff's current law, and we have currents leaving through the resistors, but we don't know what current is flowing through the 10-volt source. So this sort of complicates things. It turns out, however, that we can still get 2 equations in terms of our unknowns from looking at node 2 and node 3 together. The first thing is to notice that if we look at node 3, it's connected to node 2 by this 10-volt source. So node 3 is 10 volts higher than node 2. So this gives us one equation. We can say that V3 is equal to V2 plus 10 volts. Again, we know that because of the 10-volt source between nodes 3 and 2. So that gives us an equation. That wasn't so difficult. But to get the second equation, what we will need to do is apply Kirchhoff's current law, but rather than apply it to either node 2 or node 3, we will define what we call a supernode. And a supernode deserves to be in hot pink. So the idea is we are going to look at nodes 2 and 3 together with the following understanding. The current that flows out of this joined node, or supernode is what it's called in the textbooks. So the currents flowing out of the supernode all summed to 0. This is an extension of Kirchhoff's current law. The idea being that if they didn't still sum to 0, then somewhere in either node 2 or node 3 I would be accumulating charge, which I'm not allowed to do. So basically what I can do is apply Kirchhoff's current law for this supernode. Okay, so let's go ahead and do that. Let me define some currents, I1, I2, I3, and I4. So we'll have that I1 plus I2 plus I3 plus I4 is equal to 0. This is applying Kirchhoff's current law to the supernode. Now I1 we can get in terms of voltages that we've defined. I1 is going to be V2 minus V1 over 5 k ohms. Okay, it's the voltage at this node minus the voltage at this node. That gives us the voltage across the 5 k ohm resistor, so I divide by the 5 k ohm resistor, and that gives me the current. I2 is going to be V2 divided by 4 k ohms. Okay, so it's going to be the voltage between this node and our reference, which is V2, divided by the resistance that we're going through. I3, similarly, is going to be V3 over 3 k ohms. Okay, again, it's the voltage at this node, actually the voltage at this node with respect to the reference divided by 3 k ohms. And I4 is going to be V3 minus V4 over 2 k ohms. And this will be equal to 0. So by applying Kirchhoff's current law to the supernode, I now have a second equation that I got from nodes 2 and 3. We can rearrange this a little bit to put this in a form that might be more familiar given the form we've had before. And to do that, I'll clear that guy out of the way so we have lots of room. We have minus V1 over 5 k ohms plus V2, 1 over 5 k ohms plus 1 over 4 k ohms, plus V3, 1 over 3 k ohms plus 1 over 2 k ohms, minus V4 times 1 over 2 k ohms, and this is equal to 0. Okay, this is putting it in a form that's similar to the form we used in the, or that we have used in the previous examples. And if you look at this, this is something that you can write down by inspection, but you have to be a little careful. You have to make sure that you're looking at both voltages, V2 and V3, in the supernode. And you look at the voltages of the nodes that are connected through resistors to the supernode have negative signs in front of them. So hopefully you can look at that pattern, or look at that equation and understand the pattern. If not, you can always do it this way and then rearrange it into this form. Okay, so now I have two equations that I've gotten from my supernode. The last thing to do is get an equation at node 4, at this node right here. And that equation will be minus V3 times 1 over 2 k ohms plus V4 1 over 2 k ohms plus 1 over 1 k ohm is equal to 0. Okay, so that is the set of equations that we need. We have 4 unknowns, V1 through V4. We have 4 equations in these 4 unknowns. So now the only thing left to do is apply our favorite solver for equations to get the answer. So let's see, we'll go to Wolfram Alpha, bring up a fresh new window, and start typing in equations. We had V1 is equal to 5 volts. then V3 minus V2 was equal to 10 volts. Then negative V1 times 1 over 5,000 plus V2 times 1 over 5,000 plus 1 over 4,000 plus V3 times 1 over 3,000 plus 1 over 2,000 minus V4 times 1 over 2,000, and this is equal to 0. Okay, and then finally minus V3 times 1 over 2,000 plus V4 1 over 2,000 plus 1 over 1,000, and this is equal to 0. And hopefully this will give us a solution. So what we discover is that V1 is 5 volts, which we would have expected. V2 is minus 5.07. V3 is 4.93, and V4 is 1.64. So if we go back to our original circuit, we can write these down. So we have here that V1 is 5 volts. That's what we expected with our 5 volt source here. V2, this node here, is minus 5.07 volts. And V3 is 4.93 volts. V4 is 1.64 volts. So there you have it. We solved for all the voltages in the circuit. The thing here that was kind of tricky was the fact that we had a independent voltage source between two nodes, one of which was not the reference node, which meant that we had to use a supernode in order to get two equations from the two nodes next to the voltage source. So that pretty much wraps up this video. I hope you found it useful and enjoyable.